So our next window function that we're going to dive deep in, and one that we're very familiar with at this point because we've solved so many issues with it, last value. Return the value evaluated against the last row within its partition, the last value. So how does that work? Well, what if I want to know how my price compares to the item with the highest price in the same category? Well, let's look at what that would be like. And so over here, we can see we're doing the same select with product ID, price, category, and now we're using last value instead. And we're doing it over, and we're saying, hey, I want the last price. But you can see here, just like we did with first value, but we figured out it was unnecessary. We're doing a partition change. We're going to change the framing to be range between unbounded preceding and unbounded following. So we're still partitioning by category and we're still ordering by price, but we're going to change the frame to be unbounded preceding and unbounded following. So let's see what happens there. And so if we did last value against the price over the partition category, and we did order by price, and we said most expensive, because we need to name it right. And then we said, hey, okay, so I have this. What's going to happen, and we saw this in the previous video, is we're taking into account the previous row and the current row. So we're always going to choose the current row. So we need to go beyond the current row. And so we say range between unbounded preceding and unbounded following. And what that gives us is the ability to get the highest price in that category because we're taking into account the entire partition, not just everything before and the current row. So we're getting the actual most expensive product in that category. And unlike with the cheapest product in the category, which seemed to be $9.99 in every category, well, it seems to be $29.99 in every category here as well. Interestingly enough, there isn't much variety in pricing in this code base. So the highest price is $29.99, the lowest price is $9.99. But with that being said, what we know is that we can get the highest price. But just like with first value, is this the most efficient way to do it? No, we had to write so much code just to get this done. So maybe we could do something like max. And if we run max, we're still going to get the same value because we're still running it against a partition by category. So more efficient, less efficient ways, but whatever way works for you to get the right answer. And so with that, let's jump into the explanation of what happened here. And so if we were to look at what exactly happened here, just like with first value, we're selecting from products, we're getting product ID, price, category, and we're trying to get the most expensive thing in the category. And so to view it the most complex way, if we didn't use max, what we would be doing is we'll be sorting by category. And then inside of that category, we're sorting by price. And then we're grabbing the very last value in that category for that price. So because we're sorting inside. And the framing has something to do with this because without the framing, we wouldn't be grabbing the exact last value of the range, right? So it becomes this mental model of like, how is my window frame operating? What exactly is my window frame doing? And I find these high-level visualizations to really help understand what exactly is going on here. So try to apply these mental models when building a query with a window function, and it may help you solve for certain problems. Now let's dive into something a bit more fun, like an aggregate function that does sum, for instance. All right. So here's a nice one, sum. What if we wanted to get the sum of the values within a group depending on the framing? So we wanted to sum something, but we want to do it depending on, the partition and the framing. Well, what if I want to see how much cumulatively a customer has ordered at our store? That's an interesting question right there, right? How much cumulatively a customer has ordered at our store. So over time, how much the total becomes. And let's look at the type of query that we need to use. So we're doing a select, and we're selecting the order ID, the customer ID, the net amount from orders. And what we're doing is we're doing a sum. So we're taking the window data that we got, and we're going to partition it by customer ID. So we're creating a partition by the customer, and then we're going to order it by the order ID. And by doing that, by creating that partition by customer ID and just ordering it by the order ID, we can now cumulatively sum the amount that they spent. So it's going to go by order ID. So it's going to go look at the previous and then take the current and sum those all together. So let's look at what that looks like. So over here, I have that exact same query that we just saw where we're doing a partition and an order, and we're doing all of that stuff. So let's execute that. And what we're going to see here is we're going to see cumulative sum. So customer 1 never ordered at our store. Customer 3 only ordered for $39. But which customer ordered multiple times? Well, over here we can see customer 13 did. So the first time they ordered $227. And then the next time they ordered $83. And the sum of these two numbers is 310.76. And so with this, we can know, hey, if I were to do a where clause for a specific client, we could see how much they ordered over time and what the total amount is that they ordered, the total net amount. And that becomes extremely useful. And that has to do with how the order by works. Because if we remove this, we're just going to create the total sum of that net amount. We're just partitioning by customer number. So we're not doing anything special here. If we were to do it by order ID, if we partition by order ID, then we're going to see that, hey, it's individual based on the order ID. So the combination that we're trying to get at here is that the way that you combine partition and order can create interesting results because we're partitioning by the customer number and we're saying, hey, this is the group. And then we're saying order it by the order ID, so the individual order ID. Then we know that when we sum this, we're going to take into account the previous and the current. The previous and the current. Always remember that because that leads to interesting results. When we remove this, we're not getting anything interesting at all. We're just getting the sum of that customer ID's order. That isn't interesting at all. Like, that's just the individual order right there. What's so interesting about me knowing that specifically? And order IDs are unique as well. So what exactly is going on here? And if we look at 13, we can see, well, that's where it becomes interesting. We're just seeing the total sum of money that they ever spent. We're not seeing the cumulative sum. We're not seeing it go up. We're just seeing the total, right? So that's where order by can change how things work. And knowing all of that, let's look at how this operated internally. So if we go over here, what we can see is that we have our orders table and we have order ID, customer ID, and net amount. And to do our cumulative sum, what we're doing is we're grabbing the window that we just had and we're grouping it by the orders. So we grab the customer IDs and we said, if it matches, create a partition of that customer ID. Group those together. And then, hey, go and sort them by order ID, basically by the number of the order ID. And so what we're doing is now, because of the way that order by works and because we didn't change the framing at all. So it's going to take into account current and previous. And because order 1 has no previous, it is just the net amount of 1. And then if we look at order 2, well, it's going to do take the previous, take the current, and sum those together. And so that's how we create our cumulative sum. Super interesting, super niche. Like, when we're doing analysis against data, that's when we want to do things like this. But that being said, it's very, very important to know how partition by works, how order by works, and how introducing order by can change the entire result of what you're trying to accomplish. And so knowing these rules, knowing that when you introduce order by, you may have to play around with the framing. When you don't introduce order by, the entire partition is being taken into account. Knowing those specific nuances can help you build window functions that make sense, because the syntax can be a bit unintuitive. And so with that, let's look at the final window function I wanted to look at, which is, hey, let's try to organize it by row numbers. That's a fun little easy one. So we'll see that in the next video. All right. So the last window function I wanted to show you, and you can go and dive into the other window functions if you wanted to dive deeper into every specific one, but I wanted to give you the highest level ones, kind of show you the hitters that will give you the most bang for buck when you're starting out. Well, let's take a look at row number, a very simple one. Takes the number of the current row within the partition, starting from 1 regardless of framing. So it doesn't take into account framing. That's very important. It doesn't matter what you put there. It's not going to listen to your framing. It's just going to, boom, row numbers. So what if I want to know where my product is positioned in the category by price? Well, very simple query. We're window function masters at this point. This is easy. We got this. So we select product ID, price, category, row number. And row number is a function that you don't have to give a parameter because it's just going to generate a number for you. And so we do it over the partition by category, order by price, and we're going to say position in category by price, just to give our column a nice name. So let's look at what that does. So over here, you can see that we have our query ready to go and ready to be executed. So let's do that real quick. And what we can see here is that we are positioning it by category. So we're doing it by the price range in that category. And what we can see here is that it's not taking into account framing. It's just purely taking into account, hey, what is happening here? Because even if I said, hey, you know what? Only take into account the range between, and let's say current row and current row. I'm just going to force it. Only look at the current row. Only look at one individual row at a time. Will it change the way that row numbers act? No, it doesn't take it into account. It just ignores it. It's going to do it irregardless of your framing. It's just going to look at the category group and it's going to say, hey, this is the row number. This is where this is positioned inside of this group that you made in this partition. So that's a pretty interesting one, a pretty simple one, but it can come in useful when you want to know things like, hey, where's my product positioned by price in this category? And you don't want to go and count. Some UIs don't have this visualization. So if you're running in the command line, it may be extremely useful to use something like row number to kind of give you this visualization going on for the row numbers. All right. And with that said, we've created a very solid foundation for window functions. And I think we're all ready to do some exercises related to window functions. So let's hop into those and try those out. Hey everyone. So I hope you really enjoyed those window function exercises. And I know it was a heavier topic. It's a more advanced topic and it takes some nuance to get right. And only by practicing will we get there. So I thought, all things being fair, let's take a advanced concept, but a slightly easier one. And let's lighten the load before we hit our heavier topics again and again. And so over here, I prepared conditionals for us. A very, very light topic, very easy to comprehend, and we can do some exercises around it. And as with everything in this course, we're trying to answer a question. What if you want to select something when a certain criteria is met? Well, I hear you thinking, Mo, we've been through this. That's where the where clause came in. What are you talking about? What is this for? Well, hold on. Although the where clause is extremely powerful and it applies filtering and you can meet certain criteria to get something out, a conditional is a different way of doing the same thing. But what's so special about a conditional is you can use it in multiple places in a query. And the way that it looks is it is a case statement. So if we were to look at this, if we did select A and we did it from a table test, well, a case statement looks like this. When A is 1, then we can change the outcome of that value, the output of that value. If everyone in our database was John and we wanted to call them Jerry just for laughs, we wanted to change that output. We could use a case statement to say, hey, when their name is John, return Jerry. Or in this case, when A is 1, return 1. When A is 2, return 2. And otherwise, return other. Or you could return the original value here. And so what's useful here is that case statements can be used in multiple places in a query. Not just the where clause. The where clause is just the where clause. With the case statements, we can do multiple things. We just saw that we could change the output of the value. And I hear you saying, well, Mo, we knew how to kind of do that. But yeah, we did. But we didn't know how to do it for multiple cases. So now we can apply it against, hey, If it's this, return this. If it's that, return something else. Super useful. And each return must be a single output. That is extremely important. When we look at case statements, each return must be a single output. It must. So, rendering custom row data, we kind of looked at this. And if we look at it from the perspective of our order database, well, what we could say is we have a case, and when order customer is 1, then we return my first customer. Otherwise, we return not my first customer. Very simple. And then we always add an end to end the case, and then we show the net amount of that individual. And so with that, we have a very, very simple use case of rendering custom row data, just easily swapping out some stuff in order to render what we want to show. But then, hey, what if I want to filter in a where? And so if you're in a where statement, you can just use a case statement as if it was inside of the select like we saw here. So we could say, hey, where the case when customer ID is greater than 10, then order amount smaller than 100, otherwise order amount larger than 100. What is happening here? What are we doing? We're doing a conditional filter. That is so cool. A conditional filter. So we're saying, hey, if our customer's ID, if he's above 10, so if he's beyond 10, then we're going to only show the ones that spent less than $100. But if they're between 1 and 10, then we want to show the customers that spent more than 100. So it's a very easy way to kind of do multiple cases depending on what they're trying to accomplish. And I know we can do this with ands and ors and nots, but hey, it's a different way and you can use it or you can't. Very useful for when you don't want to divide by 0, for instance. You can use a case statement. And then the last thing we can do with case statements is we can use them in aggregate functions. So we could say, hey, only sum when the net amount is less than 100. And then when the net amount is less than 100, we're going to refund them their entire amount. So don't account for those. So there's a business case where someone comes to you and they say, hey, if we refunded everyone their money if they spent less than $100 as like a gesture of good faith, what would that look like on the total impact towards our sales? Well, then we could run a case statement that says, hey, when you've spent less than $100, let's just remove 100 from your order. Let's just give you $100 back, even if you didn't spend the 100. Let's just give you $100 back. Very, very bad for a business. But let's just say this was a case where you're going to do, hey, minus 100. Otherwise, sum the net amount. How would that impact what exactly is happening? How would that impact against our normal total? And having those two numbers, you can kind of then quickly see what are we going to incur in losses if we do this gesture of good faith. How many people spent less than $100 on a singular order if we refunded all the orders that were below $100? Very, very bad for your business. Never do this. But let's just say hypothetically you wanted to do this. Well, then you could use a case statement to accomplish this. So case statements, super useful to use across the board. And I've added some simple exercises that you can go ahead and do. They're a little lighter, a little easier, kind of fun little thing to play around with before we get back into the super, super heavy topics again. And so we just looked at conditional statements, and there's one more thing I wanted to pass off to you before we dive nose first into the next topic. Null if. So what if you would want to return a null if a condition is met? Because we just looked at conditionals, so we're pretty familiar with how this thing goes. You know, if a certain thing is there, we may want to return a null. Simple, right? Well, that's where we use null if. When you apply null if to any given statement, you're saying, hey, if value 1 is equal to value 2, so if they're equal, return me a null. It's a very, very simple function that can be used in certain scenarios where you're like, hey, if these two values match up, I just want to see null. I don't want to see anything else. Now, the scenarios in which you would want to render null depends on if you're a fan of null or not. It's a very contentious topic. If you want to show nothing at all, null is a good option. But null if is one of those functions that hey, if you want to show a null when two values match up, you don't have to go and write your own function to do it, or you don't have to go and write some complex query syntax in order to match it up with a case. There's this neat little function called nullif. So how it works is, if you use nullif 0 and 0, you're going to get null. If you use nullif ABC and DEF, well, you're going to get the ABCs. So the way it works is, if the left-hand side matches the right-hand side, you're going to get null. But if the left-hand side doesn't match the right-hand side, then the left-hand side gets returned. So you can see how you would put your column here, and then the value that the column needs to match in order to return null. That's how it works. So fill in empty spots to avoid a divide by zero issue. That's a good option. Well, if you want to fill in empty spots with a null to avoid a divide by zero issue, if that was the case, because divide by null returns null, of course, that would be an option. And there are different cases for which you may want to use nullif or you may not want to use nullif. And so we've prepared a couple of exercises for you to go through just to test out your nullif skills, your case skills, and all that good stuff. All right, here we go again, diving down the deep end. This is advanced SQL, of course. And the next concept we're looking at is called views. Now, over here, you see the icon of a mirror. It's the closest thing that I could find to a reference. You know, I could have put a view of a landscape or whatnot, but I liked the analogy of a mirror because when you look at a mirror, you see yourself. Now, that will become clear when I explain to you what a view is. What if you want to store the results of a query? Okay, this is a deep question, right? So we're running these queries. We're consistently writing new, more complex, more full-bodied queries that have all of these complex concepts in them. What if we want to restore the results of that and reuse them at a later time or query against those results? What if we want to do that? What if you want to query the results of a query? That is quite the question. Querying the results of a query. Well, this would solve a lot of issues that we tend to have. What if we want to derive an answer from a query that we ran? Well, views allow you to store and query previously run queries. And the reason I use the analogy of the mirror is because when you rerun a query, it's like looking in the mirror. You're seeing the reflection. You're seeing something that previously had run. I don't know if it's the best analogy, but it's the closest one I could come up with. But views allow you to store and query previously run queries. My analogy aside and my horrible puns aside, we're trying to allow you to store previously run queries, and that's the whole point of this. Now, there are two types of views. Two. The peace sign. Again, I like icons that depict what I'm trying to get at. So there are two types of views, materialized and non-materialized. What is the difference between these? Well, a non-materialized view, being non, the query gets rerun each time it's called on. So we're storing a reference to the query, but we're rerunning it each time that we're calling the view. So we're not actually storing the results of that, we're storing a reference to the query. Now, a materialized view, on the other hand, stores the data on the physical device. So storage, whatever storage you're using, it stores the data physically and periodically updates it when the tables change. So if you insert, update, delete data from your table, periodically the view is going to look at whatever happened and it's going to update whatever it's stored for you for when the table changes. So those are the two types of core views that we will be looking at. Non-materialized and materialized views. And the whole point of this is being able to, first of all, if I have like 2,000, 3,000, 4,000 queries, which can happen at a certain point in a company, you have so many different types of queries that you need to run. You have so many different types of answers that you need to use data to back up. So when we have that scenario where you have hundreds and hundreds of queries and you're rerunning some of them constantly, or you need to run queries against other queries, well, storing them as views can be a really, really good option. So let's take a quick look at non-materialized views. All right, so this begs the next question. If we want to make a materialized or non-materialized view, and I told you we were going to look at non-materialized views next, and we are, but first, let's look at how you actually create a view. What kind of syntax, what kind of black magic do I need to run in order to get this to work? And so the answer to that is fairly simple. What we want to do is we want to run the create view syntax, and we give it a name, and then we say as, and then we run the query right behind it. So you can pipe this syntax right here in front of every query that you've ever run, and you can give a specific view name. And what that's going to do is it's going to take that query that you're putting right here, and it's going to put it inside what we would call a non-materialized view. Views are the output of the query we ran. This is very important to remember. We're trying to be as basic as possible here. We're trying to kind of store what we ran. So views are the output of the query we ran. Also something to note, views act like tables, so you can query them. We've been in a couple of scenarios where we've ran a query and we can't quite get the entire answer out of it that we would like. For instance, with getting the current salary, which we solved with window functions. But when we ran that query and we got the last salary date, we really wished that we could have queried that and in some way derived the current salary by doing a filter. Well, here's the thing. Views act like tables, so when you create a view, you can query them, and that is the amazing part of views. And so with that, there is one third core principle that we want you to take away. Views take very little space to store. We only store the definition of a view, not all of the data that it returns. And this is true for a non-materialized view. When we talk about materialized views, we are storing the output of the data physically. Now, that being said, the majority of the time you will want to work with non-materialized views. There are some instances in which you may want to keep a materialized view around for whatever reason, performance reasons. You don't want to constantly have to rerun that query. You want it to update in the background because it's quite heavy or whatnot. There's many different reasons, but in the majority of cases, we are working with non-materialized views, and those take up very little space. Let me reiterate that, very little space. So don't be afraid of creating views. Now, updating a view. We saw how to create a view, but how do I update that view if I want to like tweak the query a little bit or whatnot? Well, that's where we use the create or replace syntax. And we give it a view name. And if the view name exists, well, it'll either replace the query if the query you're writing is different, or it will create a completely new one. So that's an easy way to update a view. And then what if I want to rename my view? What if I come into this company, right? And let's just say that they have 1,000 views, but they don't have a consistent naming convention. And because of that inconsistent naming convention, when you come in, they're like, we really need to make this easier for us. And your first job is like, hey, can you rename all of these views? We came up with this naming convention. Well, then what's your answer going to be? I can rename views like a boss. I know the syntax. Alter view. Alter view allows you to alter a view name and rename it to another view name. So we're taking a view with an existing view name and we're able to rename it to something else. Now, of course, if you had to do this 1,000 times, it would be crazy. I'm just saying for the sake of an example that let's say you had to do this. It's a fairly straightforward, fairly easy syntax to use and comprehend. And so the last thing we're going to look at is deleting a view. What if you created a view and you're like, that wasn't what I meant to keep around. Like you're cleaning out a database and there's all these views that are not useful at all. Well, the syntax is fairly easy. It's drop view. And you can optionally add the parameter if it exists. So you can kind of create multiple drops and you can say, hey, Only drop it if it exists. If it doesn't exist, don't throw an error to me. I really don't care. It may or it may not exist. I'm not completely sure. So just drop it if it exists. Otherwise, don't make a big fuss out of it. And if you were to like have to drop 2,000, 3,000, 4,000 views, you could easily create a script that would generate the syntax and wouldn't fail if you were trying to drop views that didn't exist. Fairly easy, fairly straightforward. And so with looking at all of this syntax, what we've now mastered is the basics of creating views. So let's look at actually creating views and what that looks like. Let's try some things out. Using views. So in the easiest way possible, we learned everything that has to do with views. We learned about materialized views, non-materialized views, what views are used for, kind of the general syntax that you need to use to create, update, replace, whatever you need to do. We can do it with views. We have the basic knowledge now. But just reading about something doesn't really give you the tools you need to actually use it in practice. So let's go about how you would use views. If we were to look at our use case of current salary, which is a recurring theme, I know this query has come back and back and back again, but it is because it is a good example. Getting the most recent salary of an employee in the database that we have and the way the database was modeled is non-intuitive. And we've looked at many different ways of handling it. We did group by, and it really didn't give us the correct outcome. It gave us the outcome that is correct, but when I threw that monkey wrench in there and I said, hey, what if they got a salary deduction? What would happen then? So with that, group by didn't really give us the correct outcome. So when we ran this query where we did our joins and we did our group by, we really didn't hit the mark. But what we did hit was the ability to get the maximum from date. Over here you see salary, and this really didn't hit the mark, but when we used the from date, we knew when they got their most recent salary. So we had that going. But then we said, okay, let's park this for a minute because we can't really solve it right now. We don't have the right tools yet. If I were to have a toolbox and group by was a hammer, we had our hammer, but we really didn't have our wrench. And our wrench, which, tightens the whole thing up. I'm really bad with these analogies, but you know what I'm going for. The analogy of a toolbox and gaining tools, and with the tools being able to do more and more jobs. That's the point I'm trying to get across here. Well, when we were talking about current salary and we learned about window functions, we learned that we could pull off some voodoo magic. We found a way to get the most current salary in a way that was consistent, predictable, and correct. But it had heavy computational needs. Window functions, they take time because they run against each individual record, either in a partition or against the window. So when we did our black magic, we needed a little bit of distinct going on because we wanted unique records. We didn't want duplicate records. And we wanted to use our partition, our order, and our framing in order to get the most recent salary ordered by the from date in the entire partition, not just the current and previous. So by pulling off that black magic, that voodoo, we got a great solution. We were able to answer the question. But this isn't really intuitive, So how about we try views? And what I mean is, this query, although it answers the question correctly, if I showed you this query and I told you, hey, tell me what this does, you'd really have to think about it a minute. It wouldn't be as intuitive. You really have to be enthralled in window functions. You need to really deeply understand them, which we all should, but I'm just saying there are easier ways to create queries that are more readable. So how about we try views? So if we use our create view syntax, well, then we can create a view called last salary change, where we run our query that we had, where we joined and grouped everything together, and we had our maximum from date, where we know that hey, this is the last time my salary changed. So we have now a view that has that information. Now the question becomes, well, Mo, what am I supposed to do with that? Okay, good question. like we said in the previous video, views can be queried like tables. So let's go ahead and run this real quick. All right. So here we are in Valentina Studio, and we have our query here, which is going to get us the max from date. Let's just execute it for good measure. And what we're going to see here is that we're going to get the last salary change date of each individual employee. We're seeing exactly when their salary changed the last time. Okay, so knowing that, let's go ahead and let's create a view. Last salary change. Now, if I execute this, of course, I'm going to get an error. I've already created this view. You should not get this error. So if I do create or replace view, we can just do that and it will execute just fine because I'm replacing my view with a different query. Obviously, it's the same query. So now that I have this view, what I can do is I can query it. So if I do select star from last salary change, what you're going to see happen here is I am going to get all of the same information back. But I'm querying it like a table. But it isn't a table. It's the outcome of a different query. Isn't that interesting? So we can query views like we can query regular tables. So with that being said, now, given you're all SQL masters, we've all mastered the join and everything else. Now that we have this information that we can query like a table, well, it's easy, right? So if we query star from salaries and we do a join on our view using the, well, what do we have here? We have our employee number. So we can do employee number. And now we've joined our data. Okay. So now that we've joined our data, well, what we want to do is we want to say, well, only show me the records where the from date, so the from date in salaries, is equal to the max. And why max? Because the column is called max. Because we ran the maximum and we didn't rename our column. So we want to do where from date is equal to max. And, let's just make it a little easier. Let's call this L and let's do L.max so that we don't run into any naming issues or whatnot. And so if we execute this, suddenly we are going to get the exact same outcomes. And we didn't have to use anything. And let's just quickly order this by employee number, just so that we get the right order going, because again, with relational tables, you're not guaranteed getting it in any particular order. So if we order it, now we suddenly have all of their data. We have everything. And we know the max date and we know the from date. And so, what's more intuitive, a window function or a simple query with a join syntax and a filter? Well, I prefer this personally, but some people may prefer the other. And so with that being said, it became extremely trivial for us to write the query that eluded us for so long with the group by and everything. And now we can just write a query against the view to get the right outcome. And we can keep this view around. We can say, hey, when was the last salary change? And we can make this a non-materialized view, a materialized view. It doesn't really matter. But as long as we are able to rerun it and query against it, we're guaranteed getting the right answers, even when their max salary date changes, because we're rerunning the query each time in a non-materialized view. So we have solved our issue in such an elegant way. Back over to the slides. So since we solved it in this way, here's a more elaborate form of that query. We select the employee number, the department name, the from date, the salary, and we select it from last salary change. We can do this if we stored all of that in last salary change the way that we defined it over. And so now that we know how to solve this with querying against a view, here's a more elaborate example where the join syntax is a bit different. We're joining the other way around, where we join the salary table to last salary change, which is completely feasible as well. It doesn't really matter because we've denoted each and every table with the correct identifier, and we're selecting from those specific tables specific identifiers, columns to show. So you can write this query in many different ways, but what it ends up being is we're still comparing the views max column against the from date and salaries. So it becomes extremely simple for us to do what we otherwise had to do with this complex query with the window function. And this complex query, although it gave us the same exact solution, a window function, you saw how long it took to run that window function. And of course, a group by also takes a long time, and running a non-materialized view can also take a while. But the point that I'm trying to come across here is that it's more intuitive to read a query like we did with the view join than it would be to read this, for instance. Although we are window function masters, so it's pretty easy for us either. So with that being said, this being our solution is pretty elegant. Now, let's get into some pros and cons. Pro, join syntax with filtering is easier to read. This is my personal opinion. I find it to be a big pro. Some people may find window functions easier to read. You know, pros and cons, they can vary person to person. It's like the null feature I told you about. It's a very divisive topic. I find join syntax with filtering easier to read in this case. It's easier to reason about. And this one I have a hard time saying that a window function would be easier to reason about if anyone said that, because, you know, there's more to it. There's the framing of the window function and all these other things that you need to take into account. Whereas with a join syntax, it's pretty straightforward. You're matching a column to a column and you're filtering on a column. So it's very easy to reason about. Now, a drawback, you do have to create a view. This could be a pro or a con, depending on, you know, where you stand. Do you really want to store a view for this? Personally, I would lean towards yes. Now, with all of that, do you see how easy it is for us now to write a group by function, a complex join function, a window function that's calculating all of these different things, and then just, hey, we'll store that so that we don't need to remember that query, and then we can query against it later, or we can just query it as normal. It becomes very, very, very easy to write more and more complex queries. You create a view, you create a query against that view, you may create a view of a query against a view, and you can start chaining things. Now, I wouldn't suggest you do this crazily because it becomes very hard for you to figure out, hey, which views are related to which other views, and will I be breaking views by deleting other views? You have to use it sparingly, at least in the beginning. Like, otherwise it becomes very hard for you to track down the chain of which views are linked to which other views. But that being said, views are very, very useful to write complex queries. They're a super handy tool. With all of that, what I want to leave you with is a couple of exercises that you can go try out against views before we dive into the next part of views, which is updatable views. During this next portion, when we talk about indexes, we are going to be heavily leaning on some theoretical concepts, because creating indexes is a pretty straightforward command, but there's a whole lot that goes into deciding where, when, how do I make an index? Why would I make an index? It's more of a decision-making process. It's like the iceberg where you see the top above the water, but there's all of this depth below the surface of the water that you need to know. So even though it's going to be theoretical, I promise it's going to be amazing. Now, let's get into it. What is an index? An index is a construct to improve querying performance. So we're trying to improve query performance. That is the quintessential purpose of an index. Now, if we looked at it from a more theoretical point of view, it is a pointer to data in a table. Right? It's kind of like you saying, okay, here's my piece of data, and here is an easy way to reference it. You're basically telling the system, hey, make this more important. Keep a reference to it just so that you know how to handle it. It's kind of like indexing your hard drive, if you've ever done that, is an ability for you to be able to type faster in the search bar and find files faster. Indexing is a process of you saying, hey, keep a reference of all of this stuff so that you can handle it more quickly. So think of it like a table of contents that helps you find where a piece of data is. A table of contents is nothing more than the ability to say, hey, in section A, you can find this, in section B, you can find this, and you often do this. When you're writing a paper or when you're writing a book, you'll put a table of contents in there to help people reference certain portions of the book to make it easy for them. Think of it like that. It's just a way for the system to know, hey, here's a fast way for you to access where a piece of data is. And so the sole purpose of it, and this is supposed to be a speedometer, is for you to speed up your queries. You want them to go faster. Sometimes you'll execute a query and it'll be a bit slow. And so depending on the tables, the amount of columns, and so forth and so forward, you may want to index certain pieces of data to speed up the queries, because speed is important. You don't want queries running 30, 40, 50, 60 seconds. That's just going to be painful. Like, you want your queries fast, like a Maserati fast. Now, it does slow down data insertion and updates. What do I mean by that? Okay. For every benefit, there is a cost. Nothing you get can come without having a downside. And so the downside of indexing is, if you add an index on certain columns, if you're adding a table of contents against category and price and so forth and so forward, well, it's going to be very fast to look up against those once the data is indexed. But now, let's say you're going to insert 10 million products, or you're updating 10 million products. Well, because it has to keep that table of contents. Well, when you insert an update, just imagine you having to go back to your table of contents and being like, all right, I added this and I added this and there's new data over here. It's going to slow down the insertion and updates. Now, in most cases with minimal amounts of data, it's going to be trivial, but like we're talking millions and millions of records here. Well, yeah, it could take a while. It's going to slow it down because you have to update those tables of contents. So every action has a reaction. And in this case, it's a negative reaction. You're going to slow something down in order to get those gains. Now, one thing to note here is that when we talk about indexes, there's many different types of indexes we can apply. You can apply a single column index. This is very straightforward. It's very self-explanatory. You're applying an index against a single column. You can apply a multi-column index in which you're applying the index to multiple columns together. So the reference, the table of contents, is referencing all 3, 4, 5, 6 pieces of data, even 2, 3, 4, whatever the number is. It's more than one, is what I'm trying to say. You can have a unique index. A unique index means that there can be no two of the same values within that index. That table of contents has to be unique. And when we think of this, we obviously think of the primary key, because the primary key is the unique identifier. So that's a good example of a unique index. And you can apply a partial index. You can say, hey, I only want part of this data to be table of contents. You can apply an index against a part of your data. And then you have something called implicit indexes. Things that automatically will be indexed because, hey, Postgres, MySQL, whatever database engine you're using, they're going to index this by default. It's going to be done by default. So knowing all of that, let's look into some of these. But first, how do you create an index? Well, over here you can see the syntax. Create, and then you can potentially add unique. So this is an optional keyword. So you can create index, and you can give the index a name. So giving the index a name gives it a unique name. And so those naming conventions, well, when we create indexes, you have to create a naming convention for your indexes. Otherwise, it's going to become very confusing for you to know, hey, what is an index and what isn't. Naming convention could be to preface every single index with IDX underscore. So you create potentially a unique index or just a normal index against a table. So you're creating it against a table. So you give it a name and then you say, hey, create this index on, for instance, what tables have we used? Employees, salaries, or whatever else. But then comes the most important part of the index. Telling it which columns it's supposed to apply the index against. And when you create this index, Here is where you're basically going to determine if it's a single or a multi-column index. If you add 2 columns or more, you're creating a multi-column index. If you only say 1 column, you're creating a single column index. How do you delete an index? You drop index and you give it the name. Very straightforward. And now comes the most important part. When do I use indexes? Well, we always index foreign keys, and we always index primary keys and unique columns. So any column that could contain unique pieces of data, like columns that can only get certain inserts, they have to be unique. Well, we're going to index those because they're unique, so we don't have to keep a table of reference against that. We also always index on columns that end up in the order by or the where clause often. Now, this is the most important one. When you're writing queries and you're writing hundreds and hundreds and hundreds and hundreds and hundreds of queries, and your entire team is cycling through and you have this backlog of 1,000, 10,000 queries, you figure out like, hey, let me sort through these and let me go look at some of them. And you find out that there's an order by and where clauses. There are columns that are often in there, but they aren't indexed yet. Well, we should index those because you're going to speed up all of those queries by default. Now, these are decisions that need to be made either ahead of time or later in time. It really depends. Like when you're making a database, it's often difficult to assume what's going to end up happening. You can do a lot of ideation up front, a lot of design up front, and the more experience you have, the more intelligent decisions you can make about how to structure the data and what to index and what not to index. But if you're starting off your journey and you're initially making a database, well, go with the defaults, index the primary and foreign keys, and then start writing your queries and figure out where you can optimize. But view it as a learning curve, view it as a journey, and don't view it as trying to do too much up front because you may end up over-architecting your system. And that's also not good. And so then we get into, when do you not use index? Don't just add an index just to add an index. I can't stress this enough. Don't just throw indexes around because those table of contents that you're generating, well, they're heavy and they need to be updated. You're slowing other things down. Don't just add an index to add an index. Don't index on small tables. If a table only contains X amount of records, thousands of records, not millions, don't index on small tables. And the definition of small can vary depending on the size of your database and how much you're working with. And there are different techniques for larger databases, but just don't index on small tables. And I know that when you're working with that database, you'll know what a small table is versus what a large table is. Don't use indexes on tables that are updated frequently. When there are a lot of inserts and updates happening on a table, don't just add an index to columns on that table. Because if they're updated frequently, that means the system has to spend time reindexing and reindexing and reindexing. And don't use it on columns that can contain null values. Because if they're nullable, it may just hurt the index's speed. Also, do not use it on columns that have large values. Don't go indexing if you had, for instance, a review system, the comment section. Because comment sections can contain comments that have 500, 600, 700 characters. Don't use it on columns that can have large volumes of data in them. Large values are hard to index. So keep these in mind when trying to decide when or when not to create an index. And so now let's take a look at some of those types of indexes that we looked at. Now we're getting to the good stuff. We're going to look at the different types of indexes that occur when you want to execute queries. And we're also going to create an index to illustrate the performance improvement that you can gain. So, first up on the chopping block, single column indexes. Single column indexes are indexes that are used against the most frequently used column in a query. The most frequently used column is often the column that you are referring to in every single query in the where clause. So that's the column that you are going to apply an index against. Then we have multi-column. Multi-column is the same as single column, but you're applying it against a group of columns in a query. So multiple columns. The important distinction here is that it really depends on how elaborate your where clause is. When you use a multi-column index, you're using it against multiple columns. So you're using it against columns that happen to be used in multiple queries in the where clause. If you're filtering against, let's say, a category and a type, which in essence are kind of the same thing, but let's just say for nuance sake that you had a table where you had a category and then a category type. Well, then let's say you had a where clause and you had 100 queries that were using those two and they didn't happen to be indexed in any way, shape, or form. Well, you're going to use it against that. Then you have the decision to make of when you're going to use a specific index. So when are you going to use single column? Well, if you're retrieving data that satisfies one condition, so you're always trying to satisfy one condition, then you're going to use a single column index. Multi-column is when you're retrieving data that satisfies multiple conditions. Again, a where clause that is trying to apply against multiple cases. You're having ands or ors, stuff like that. Then next up are the unique indexes. Unique indexes are for speed and integrity. When you create a unique index, you are also creating an integrity check. You usually create it against columns that can be unique. So always use a unique index against a column that can only contain unique values. And these are built for speed. Next up, the partial, an index over a subset of a table. So this one is interesting. When you create an index, you can create an index with a specific name on a table, and you can give it a specific expression. You could say, hey, do it only where the salary range is over 5,000, for instance. You can apply an expression like that. So the partial is over a subset of a table. Now, then we get into the implicits. Implicit indexes are created by the database. The database automatically creates these. When does it create them? Well, let me give you two examples right here, right now. When you create a primary key or a unique key, so you flag a column as primary key or you flag a column as a unique key, the database is automatically going to index these. Why? Because it's a good, solid decision that you should always apply. So the database is already going to do it for you so that you don't have to worry about it. All right, so let's create an index just to showcase. Over here, we're in Valentina Studio. And you can see that I have a query where I'm selecting the name, the district, and the country code from city in the world database. And I'm applying a filter. I'm saying where country code is in TUN, Belgium, or the Netherlands. So I'm applying it against specific country codes. And as you can see, I'm getting 8 back. But there are a ton of records. There's 4,000 records in here. Now, you may think, well, this query executes relatively quickly. Let's look at it real quick in detail. Explain, analyze. A keyword that you can put in front of any query to explain or analyze the execution of that query. And if we execute that, what we're going to see is we're going to see the query plan. What it's going to do, it's going to scan on city. It's going to filter based on our filter here. And it's going to remove rows that don't match. So it took 0.115 milliseconds to plan, and it took 1.3 seconds to execute. Now, if we look here, and we look at our schema, and we look at city, the table specifically, we can see there are no indexes on this table. So there are no indexes. This column is not indexed, nor is it unique. It's not a unique column by any measure. But it took 1.3 seconds to execute. Now let's say we created an index against it. Create index, and let's call it IDX country code. And let's do it on city. And then let's do it on the column country code. All right. When we do that and we execute this, and then we go here and we refresh, we'll see our IDX country code. Now let's execute that same query again with the analyze. And what we can see is that our query plan changed. Why did our query plan change? Well, it's using the index. It's using the index to apply the condition to. So even though our planning time stayed the same, our execution time went from 1 second, 1.3 seconds, to 0.3 seconds. That's a massive, massive, massive gain. And so indexes can really, really speed up queries. But again, you have to take into account when and how to make a decision and what to index against, because insertion against this will make it very difficult for us to update and continuously change, because now the index needs to be updated. And it's not to say that it's a super, super heavy operation in this specific case, but it can be. And if you have millions and millions of records, creating an index can take a long time, for instance, depending even on the type of data that is stored in that index. But what we see here is very clear cut. Index speed up our queries. We just need to be smart about them. Now let's look at creating a partial index, for instance. Now this is going to be a very contrived example, but let's quickly delete our index that we created. And let's say that we went ahead and we created that same index. We create index IDX country code, and we do it on city, and then we do it on country code. But then we say where country code in, and let's take our 3 examples here, and let's do it against those. So let's execute this. And now what we have is a partial index. So it's only going to index the ones that appear in this list, which will optimize for our query. Let's see what happens when we execute our query. So let's take this and let's do a select country code from, and then let's do city, and let's do our where clause again, and let's take some other stuff. Let's do name and district. So let's select name, district. And as you can see here, name is a reserved value. So, we'll put it between double brackets just so that we reference it correctly. So here we can see this. And if we run our explain analyze, of course, our query execution time is going to be extremely low because we've indexed specifically against these 3. But let's throw a wrench in there and let's take PSE and Sweden, and let's take the USA. And let's see what happens here. Our execution time is 1.9 seconds, and that's because our index is partial. But what if we threw Belgium back in there? Well, it's not really going to matter because the index is against those 3 specific values. If we went ahead and we deleted our index again, and we just applied our index fully, we said, let's create our index again, and let's say IDX country code. And we're doing it again on city, and we're doing it against country code. So we're going to create the full index now. And then we run it again. Well, we'll see that it goes down. It's not 1 second anymore. So partial indexes go against what you would consider a part of that column. So part of that column is going to be indexed. And when you run a query against part of that column, that part is going to execute extremely fast. But if you change the criteria in your where clause, well, then it's not going to use the index to search, of course, because that part is not indexed. So it'll slow down again. So hopefully you can see the benefits of creating indexes here. But there's one more thing we need to take into account. These indexes we're looking at, well, when we look at how computer science works, usually when you create a table of contents and you're creating search algorithms and you're searching and you're filtering, there are specific algorithms that we use to optimize for certain scenarios, because a different way of searching may yield quicker results depending on the situation you're in. So let's look at some of the algorithms that can be used for indexes. Perhaps the most important question of all: when do I use a specific type of index? Now we've looked at single column, multi-column, and all of the different types of indexes you can create. But backing an index is an algorithm. And an algorithm is nothing more than a set of instructions that tells the query how it should find something, right? How it should particularly apply a faster lookup. Because indexes are all about speeding up your lookup, and the algorithms backing it are applied against different types of data. So when we store data in SQL, we all know that any different type of data may need a different type of lookup. Numbers 1 to 100 can be indexed very efficiently using a specific algorithm, but if we say had 700 line pieces of text, how are you going to create a table of contents for that? Could you imagine manually creating a table of contents for things that contain a 700 line of character set? Creating a table of contents for that, if you had like a review column, for instance? Well, that's where algorithms come into play. And Postgres provides several types of index algorithms. And each one of these algorithms is tailored to create an index that is going to speed up a query that is doing a specific type of check or contains a specific type of data. And we're going to look at how to apply each and every one of these individually and what their strengths are. Now, over here we can see we have the B-tree algorithm or a B-tree index, a hash algorithm or a hash index, a GIN algorithm, also known as a GIN index, and a GIST algorithm applied to a GIST index. And each index uses, again, a different algorithm. That's why they have different names, of course. And the main question you have is like, well, Mo, okay, I get it. There are different types of algorithms. But how do I even go about creating an index with one of these specifically? I thought you just showed me the create index syntax. Good point. Extending on that, when we look at the create index syntax and we have this optional and unique keyword, when we apply a name and we say do it on this table, we can specify, hey, do it using this specific algorithm or method, and then apply it to these columns. So let's look at how that would look. So here we are back in Valentina Studio. We had this query where we were trying to optimize against the lookup in specific country codes. And so to do that, we were creating an index called IDX country code. And if we go look at our table, what we ended up seeing was that we had no indexes. So if we refresh this and we execute on city and we apply it to country code, what we're going to see is when we execute this and we create our index, and if we refresh here real quick, we now have an index on IDX country code using the B-tree algorithm, which is the default algorithm. And what we saw happen here is when we applied explain analyze to analyze our query, we saw that our query was significantly faster. Now, let's say that we wanted to use a very specific algorithm. Well, let's go back and let's delete our index. And once we delete our index, we can create it using a specific algorithm. And let's see what happens. So if we say using, for instance, the hash algorithm, and we apply it to country code, this is how we would do it. We would say create index IDX country code on the table city using the algorithm hash on the column country code. That's how we would read this. And if we execute this, now if we refresh here, what we'll see is that if we go into design, it's now using the hash algorithm. But how does this impact the speed of our explain analyze? Because using the B-tree algorithm, we were at 0.2 seconds. So let's run that. And what we can see is it really didn't help our query performance. The hash index isn't used to speed up the type of query that is using the where in. The B-tree algorithm, on the other hand, sped it up to 0.2 seconds. So each one of these algorithms has a specific use case. And so let's look at when you should use them. So this begs the question, what we just saw. When should I use which algorithm? Now, the B-tree algorithm, as we said, is the default algorithm. and it is best used for comparisons with greater than, less than, between, in. In is the one we were using in our query. Is null and is not null. So all of these are specifically performant with a B-tree algorithm index. So the default algorithm would have worked best for the in, and we saw that because it was 0.2 seconds. But then if we look at the hash algorithm, well, the hash algorithm can only handle equality checks. So an equals. If we did an equals operation, we might have an extremely performant query. So let's go look at that. So over here we are back at our query, and let's try to do it with an equality operator. So if we did equals bell and then an and country code equals TUN and country code equals NLD, let's see what happens. What will the explain analyze say? We are at 1.15, remember? That was when we applied the hash algorithm. So let's see what happens. So now we're at 0.028. So that is super fast. The hash algorithm went from 1 second to 0.028 milliseconds. That's how fast the hashing algorithm can figure out the equality operator. So it's even faster this way than when it was with the in operator and the B-tree algorithm. Are you seeing now how specific algorithms can actually speed up a query significantly? The execution time here is ridiculous. Now, obviously, we don't want to write a query like this very specifically, but again, when you're dealing with millions and millions and millions of records, the algorithms you choose to use against specific queries may dictate how you want to write that query, if you're going to use the equality operator or not. So determining what index and what algorithm to use may dictate the way that you want to write those queries. You have to take the algorithms into account when you're writing the query that has a hash index. It's crazy how much an algorithm can dictate the speed at which a query will execute. And as we saw here, the B-tree algorithm is fast, but the hash algorithm was super fast. Now, with that said, let's look at some other types of algorithms that can be used. GIN, Generalized Inverted Index. It is best used when multiple values are stored in a single field. Now, we haven't really seen any columns that store multiple values in a single field, but when we get into database creation and table creation, what we're going to see is that Postgres has an array type. And we'll get into the details of what an array type is, but basically what an array type is multiple values in a single field. So we're storing multiple different values inside one cell of one row of a column. So multiple values in a single field. And that's where you can use the generalized inverted index. That's where this one shines. And then the last algorithm I wanted to show you when or how to use is the GIST algorithm, the generalized search tree algorithm. And this one is useful when you're trying to index geometric data or full text search. So if you are trying to do something where you're trying to search against, for instance, you had a database where people are leaving reviews and you wanted to search against specific keywords in a review to see, hey, is this good, bad, whatever? Well, that's where if you needed to write a query to search for specifically that, the GIST algorithm would be your best bet because you're doing a full text search against a field and it could be quite heavy to index in a different way. That's what the generalized search tree index is for. Now, knowing all of this and knowing when to use which algorithm is extremely beneficial to applying the right type of index. Applying the right type of index, as we saw, can speed up your query tenfold depending on what you're trying to accomplish. Do I choose hash? Do I choose B-tree? Now, don't get overwhelmed. These decisions should not be made easily, and research should always be done, and the decision should never be made lightly, and usually it should be made with a team, and it should be a discussion. Now, with all of that said, creating indexes can supercharge your queries, and it is so important to know. Now, we've mastered indexes. Okay, that's kind of an overshoot, but we know when to use which indexes and we know how powerful they can be. And so it's extremely important to keep this in the back of your mind when you're running against queries that are running slower and slower and slower. Indexes can help you out. With all of that said, let's dive into subquery. Welcome back, everyone. So now we're going to take a look at subqueries. Subqueries are one of those concepts that actually allow us to do complex things. Now you may be thinking, why did I choose this icon here? What does a hot dog have to do with a subquery? Well, let me explain that to you real quick. It's very, very hard to find the right icons for the right concepts. And so when I was looking for subqueries, I kind of thought to myself, well, there's not really going to be an icon that matches the description of what a subquery is. Well, maybe there is. But the first thing I thought about was, well, a subquery is a query inside of a query. Kind of like a hot dog in a bun. Now, what do I mean by that? To be honest, I don't even really know. But I thought it was funny. I liked the icon. So I picked it to describe what subqueries are. Now, the flaky analogy aside, a subquery is a construct that allows you to build extremely complex queries. And that's what we're aiming towards. Not my bad analogies. We're aiming to build complex queries. We're aiming to become masters of SQL. And so a subquery is also called an inner query or an inner select. So let's pause for a second and think about that. A subquery is a query inside of a query, and it's also called an inner query or an inner select. Now that's interesting because what we're trying to achieve with subqueries is the ability to utilize other queries inside of our current query to build stronger, more complex queries. And subqueries are one of those concepts that can be often abused. They can cause performance lag. You have to be very smart with how you approach subqueries. Now, a subquery is a query within another SQL query. We've already been through this. We know it's a query inside of another SQL query, right? But what we didn't know is it's most often found in the where clause. So it's most often found in the where. With that knowledge, well, we're already masters of the filter. So how would we use a subquery to extend the where clause? Well, let's say we had a query where we're selecting star from a certain table and we wanted to do a condition greater than, less than, in. We have all of these conditions that we learned with filtering and we have a specific column. But the thing that we want to compare against, well, that becomes more tricky because in a where clause, you can see here, column. In a where clause, we're only comparing against a singular value, right? So in a where clause, a subquery should actually only return a single column, not multiple columns. Even though it is called a subquery, it cannot return multiple columns in the where clause. On top of that, when we use a where clause to do a subquery, well, then we need to compare against something. And so we'll get into the specific examples of the utilization of a subquery inside of the where clause and how that looks. But there are very specific rules. And why would we use it with a where clause? Well, we haven't answered that yet. Well, let's say that we ran a query and that query returned us a column that told us something specific, like the maximum salary, the maximum age, so forth, so forward. Something that we couldn't really derive through a join or something else like that. Well, that's where we would use a subquery in our where clause. We're basically trying to filter against a result set, a row set, or a singular result. For instance, the average salary, where the salary is larger than select the average salary from salaries table. That's a possibility. So subqueries can be used to filter in smart ways in the where clause. But you can also use the select, the from, and the having clause to run a subquery. All of those parts of the query are also accessible to subqueries. Now I see you gasping with your mouth open like, is this true? Well, it is. And it would look something like this. If you were to use it in a select statement, you could select from a subquery. So, interestingly enough, it must return a single record. It must. Because we're going to use it against every single row in a select statement. So it must return a singular value. What returns a singular values? Well, our aggregate functions. Sum, min, max, average, those types of things. Limit 1, for instance, could return if we ran a limit against a query. So there are different ways of returning a single record, but when you use a subquery in a select statement, it must return a single record. When you use it in the from clause, well, that's where it becomes more interesting, because you could select everything from a subquery. So you could, for instance, run a subquery that's doing something more complex and then select from that. It would be kind of like selecting from a view. We're basically technically selecting from a different query that is running in the background. And why would you do that? Well, for instance, if you only wanted to select a subset of something that already ran a calculation or so forth or so forward, a subset of a subset, those are all valid reasons to use a subquery in the from clause. And if you use it in the having clause, again, it must return a single record because we're trying to compare against something. If you're trying to use a group by and you wanted to compare against, for instance, an average, a sum, a min, a max, you have to return a single record. That also means that you can only use one column, not multiple columns. That is not possible with the subquery, even though in a subquery, it is a query. So technically speaking, you could run a subquery with multiple columns, but because you're returning a single record, you're usually going to be using one column, not multiple columns. And so with the having clause, what we're trying to do is we're trying to compare for the groupings. So we're trying to filter down our groups. Now, one thing to note about these types of subqueries, the ones that aren't in the where clause, well, people argue that these aren't true subqueries. They say, hey, if it's not inside of the where clause, it's not a true subquery. This argument has been thrown around. You'll see it thrown around online if you Google or whatnot, or maybe someone on your team thinks that. And to that I say, potato, which is an English way of saying, hey, it doesn't really matter. Why argue these types of semantics? If it's a query inside of a query, it is a subquery. And let's not dilute our learning process with these semantics that overcomplicate things, specifically the ones that are rooted in people's opinions. So, I hear you saying, wait a second, Mo. If you're using a query to query different tables, how is a subquery different from a join? Can't you just technically use a join to join data from two tables? That's a good question. So let's look at some of the differences between a join and a subquery. Let's take a look at some of the differences between a subquery and a join, otherwise known as the hot dog versus the chain. My analogies are really, really reaching at this point. But what I'm trying to get at is, when we use subqueries versus when we use joins, what are we trying to accomplish? And so when we look at subqueries and joins, both subqueries and joins combine data from different tables. So they're trying to pluck data from somewhere else and use it in the current query. But subqueries are queries that could stand alone. Let's take a look at that. Over here, we're in Valentina Studio on the store database. And over here, you can see I'm doing select title and select price. And I'm selecting the average price from products as the global average price. Now, if I run this, what I'm going to see is that I am running a separate column over here where I'm grabbing the average price, right? And so I can compare my current price against the average price of all products. But what we mean by this, what we mean by subqueries are queries that could stand alone, is I could really technically grab this. I could comment all of this out, and I could run this on its own. And it would give me the global average price. It is still just a query, right? It's just a query. But if we look at something like a join, well, when we use a join, what we're technically doing is, here you can see I'm doing the same on the store database, and I'm selecting the product ID, the title, the price, the quantity in stock from the products. But I couldn't say remove this and run join. Like, what would that do? I would get a massive error, syntax error, because a join is part of a query. It is not something that could live autonomously. So subqueries are queries that could stand alone. That is the imperative here. But joins combine rows from one or more tables based on a match condition. See, they're matching against something. They're saying, hey, where the product ID is equal to this product ID, or where the employee number is equal to this employee number. You're combining tables based on a matching condition. Where subqueries, they don't really need to run against the match condition. They're just queries. So subqueries can return a single result or a row set. Now let's take a look at that. So over here, we're back in Valentina Studio, and you can see that I'm running the same query that I did before, where I'm calculating the global average price and comparing the price against the current price of the product. Now, we know that when we use a subquery inside of the select, we need to return a single row. Otherwise, things may break, because if I took away average price and I just did price, okay, well, what now? Oh, one or more rows returned by the subquery expression. So inside of the select statement, it is not allowed. But if we did say select, for instance, in the from, and we ran the exact same query, select star from products, well, what we'll see here is that it will work. Now, it must have an alias, so let's give it an alias, products sub. And what we'll see here is that it'll just work. So depending on where the subquery is being run in the query, it can return either a row set or a singular result. This is a singular result. This will return the entire row set. And how do we know this? Well, because we're selecting everything from products. So we're selecting everything from products, and then we're returning everything that we have. Now, if we wanted to say where the price was greater than 20, now we're filtering and we're only showing products that are above $20. We're not showing any products. Now, if we said it had to be less than 10, well, then our entire result set is going to be less than 10. So we are returning multiple rows from this subquery, but we're returning a singular one from here. So what we're trying to say here is that a subquery can return one result, or it can return multiple results. That mental model is important to know. And depending on where you use it in the query, if you use it in the select, you have to return one result. We saw that. But if you use it in the from clause, you can return multiple rows, and then in the from, it'll just use it as the data that it's going to feed for the select to select from. Now, that is important to know. So subqueries can return a single result or a row set. Now, joins can only return a row set. They're only capable of returning the combination, right? We looked at joins. You have inner joins, outer joins, and the intersection of data always returns you the combination between A and B, table A and table B. So you're always returning a row set. You're never returning a single result from a join. You're combining two tables together. Now, another thing to know here is that a subquery's results are immediately used. They're immediately shown on the screen. Like, you cannot use them in a different way. Whereas a joined table can be used in the outer query. Now that's interesting. Let's look at that real quick. over here, we're back in Valentina Studio, and you can see that we were selecting title price, and we selected the average price over here. And we can see that we're able to visualize from the subquery the output itself. But we can't go and say reference this in different parts of the query. Whereas if we look at our join, when we use a join, right, we're saying join inventory, which is an inner join, and we're saying using the product ID. And then we're able to reference the inventory as an alias, for instance. We don't necessarily need to do this, but we can reference parts of the join. We can reference data that was joined together from different parts. So we could say, hey, get me the quantity in stock of inventory because I joined together this table. So I can reference things from the join. That is completely possible. Now, these are extremely important facts to know about subqueries versus joins. Joins are not standalone. Subqueries are still queries. They execute like normal queries do. So you have to approach them in different ways. And it's important to know that deciding when to use a subquery versus when to use a join is an extremely difficult choice. This is what separates the professionals from, say, juniors. The ability to decide, hey, am I going to use a subquery? Am I going to use a join? Hey, let me analyze the way that this outputs and let me figure out ways to make more performant queries. And experience reigns king here, especially experience when it comes to data modeling and putting together your database, or understanding when to use what in certain scenarios or when to add indexes. All these decisions are what separates what we would consider a junior from what we would consider a senior. So it's important to practice subqueries and practice joins, and then start to understand when you should use a join versus when you should use a subquery. Now, one thing I can give you is if you're able to use a join, always use a join, because generally speaking, they will be more performant than subqueries because subqueries still need to execute that query. So with all of that, it's important to continue to practice these concepts. Now let's look at some cases of using subqueries. So far, we've learned so much about subqueries. No pun intended, my hot dog analogy did not really work against this, but I keep bringing it back just to slightly laugh at myself for coming up with this horrible analogy. But moving on from that, what I wanted to dive into is some general guidelines that you may want to follow when using subqueries and that we've seen throughout the videos, kind of rounding out our knowledge here, because it's important to know when and how to use subqueries and exactly what rules to follow. And so one of the first guidelines that I wanted to discuss is that a subquery must be enclosed in parentheses. This is one of the hallmarks of using a subquery, is that you use those parentheses to denote that you're going to run a subquery. Another one is that it must be placed on the right side of the comparison operator. So when we apply a comparison operator, when we use subqueries in the where statement where they are often used, it is important to always put the subquery on the right-hand side of the operation. Subsequently, you cannot manipulate the results internally. What do I mean by that? When a subquery runs, a subquery has its own context. It has its own result set. But that means that whatever returns up to the parent query, you cannot manipulate it. So if you run an order by, for instance, inside of a subquery, it's going to be ignored. You're not going to be ordering that result set. And so with all of those guidelines, we kind of bleed into the next one. We always use single row operators with single row subqueries. What do I mean by that? Well, when you use average, min, max, or whatever, we generally are going to use the single row comparators equal to, less than, not equal to, against the subqueries that are going to return a singular result, min, max, average, for instance. And then one of the last ones that I wanted to run through is that subqueries that return null may not return any results. So if your subquery returns null, depending on what operators you are using, it could be that that null causes the entirety of the comparison to return null and thus return no results at all. So be careful with subqueries that return null. And so with all of that, I wanted to dive into the types of subqueries that are available when writing subqueries, but we really haven't denoted them with a specific type. So let's look at single row, multiple column, correlated, and nested. These are the types of subqueries that you may see from time to time. When we run a single row subquery, what we are trying to do is we are trying to compare, for instance, the salary against a single returned row. So min, max, average, those aggregate functions that boil down a number to one single record, those are the ones that we would use to do a single row return. So a single row subquery returns 0 or 1 row. And so the point of these single row subqueries is to do comparisons against your where statement. So here we're checking, hey, check where the salary of my employee is equal to the average salary in general in the company. Another usage for single row subqueries could be, for instance, in the select statement, where, for instance, we add it as a extra column to each and every row. So by doing this, what we're doing effectively is we can compare the average salary against the baseline salary of each individual employee because it returns 0 or 1 row. Thus, it can operate kind of like it did when we were looking at window functions. Then we get into multiple row. This is where the subquery is returning multiple rows of data. It's not just a single row. And in that case, we need to use different types of operators. For instance, we could use in. Here we're checking where the category is in comedy, family, and classics. Now, I could have written the in statement against a category number sequence, but I don't necessarily know which numbers correlate to which categories. So it's easier for me to write the subquery where I check against the specific values that I'm aware of. But the point is not that this query is useful. This is kind of a redundant subquery. You could have made this easier. But in any case, it's to showcase that you can use subqueries with multiple rows and check them against the parent query with stuff like the in keyword. But the whole purpose of this is to think about the subquery and see, hey, is this subquery going to return one or multiple rows? In this case, it would return 3 rows, comedy, family, and classics. And it would return the category number for each of these categories. Thus, I can check if the category from my product is in one of these categories and filter like that. Next up on the chopping block is multiple column. This is where a subquery returns multiple columns. Over here, we can see that I'm selecting employee number salary, and I'm selecting the department average salary by doing a join against a subquery. And that subquery happens to be the combination against a different join. So I'm using the salaries table and I'm joining against the department employee table. And then I'm joining against a subquery where I'm selecting the department number and the average salary for that department, where I'm grouping by the department number. So I'm calculating for each department the average salary. And by doing this, what I'm basically doing is I'm creating a result set in memory. I'm creating a multiple column table in memory from this query. And then I can reference it by giving it an alias. And then I can join against it against the department number because the department number is available through the select statement. It's like me building a table through a query in memory. And I can just join against it. And SQL in the backend is going to kind of take the average salary, which I did not denote with the specific name, so it's going to be called average or AVG. And what I can now say is, hey, give me all of the employees where the salary is larger than the department average salary. So I can see every employee that has a salary larger than the department average. And then I can also reference, because it's a join, because I'm using a join against the subquery, I can reference the alias I gave it, and I can view the average beside each and every row. So what it comes down to is that the basis of this is that you can write subqueries that do different things. They can return a single value, they can return multiple values, they can return multiple values across multiple columns or single values across multiple columns. But the whole purpose of this is to understand that subqueries are just queries, and the way that you write that query impacts the way that it's going to come out into the parent query and how the parent query needs to work with that. And at the end of the day, what we're trying to achieve here is different ways to answer different questions. Now, the next type of subquery is correlated. Correlated is a popular type of subquery, but it changes the way that the subquery operates. Because if you remember, we talked about subqueries being queries that can be run on their own. They're just queries. Well, when we create correlated subqueries, what we're doing is we're creating a query that references one or more columns in the outer statement. Okay, what do I mean by that? Well, over here you can see a subquery where I'm running a where. So I'm running a filter and I'm saying, hey, filter my from date where it's equal to the max from date from salaries where the employee number is equal to the current employee number. So I'm creating a subfilter of all of the records of that current employee, and then I'm going to select the max from date. And the way I'm drawing the relationship is by referencing the outer employee number. You see it right here, s.employee number, which references the outer query's employee number. Now, one thing to know about correlated subqueries is when you write them. This right here, this can become a performance bottleneck if you're not careful. Now, why do I say that? Because when you correlate a subquery, when you say, hey, subquery, take into account the outer query's information, well, now the subquery has to run against each individual row. So there's more processing that needs to happen in the backend for the query to execute. Now we're, in essence, creating groupings by using a subquery's where statement. This isn't the most optimal way to solve this question, but it's also to showcase that when you create a correlated subquery, you have to be very cognizant of what the runtime complexity is going to be. How long is that query going to take to execute? It's not to say that correlated subqueries are bad. It's just to say that we need to be mindful when correlating subqueries. If you can solve it in a way that you do not need to correlate the information to the outer scope, that is great. In this particular case, this is one way of solving this question that takes a long time to run, but solves the question correctly. And then we have nested subqueries. These are subqueries inside of subqueries. And over here, you can see this query isn't doing anything particularly special. What it's basically doing is it's creating a join of a subquery that is in memory that is trying to get a limited scope of products that are in specific categories. And then by joining them against the order lines, you're going to get the order lines for those specific products. Do you need a double nested subquery right here? Not really. It's not super useful, but it is a way to write this. I wouldn't say it's particularly a good way, but it's to show that you can run a subquery inside of a subquery. All right, so let's put the hot dog in the bun and get to subquerying. Somehow in my head that sounded cooler than me actually saying it. What we're getting at here is we're going to go through some of the examples of subqueries. Now, when we get into using subqueries, what we want to do is we want to solve for complex scenarios. That's what we've been doing all along, right? We need a question to answer, and when we get that question, we can build a query around it. Otherwise, everything kind of stays abstract, and I don't want to ram theory down your throat without giving you practicality. So let's look at our first query. Show the employees older than the average age. Okay, so let's take a look at how to do that. So over here, we're back in Valentina Studio, and you can see we already wrote out the query. It's select first name, last name, birth date from employees, and then we're saying where the age, so we're using a date and time operator to calculate the age of birth date is greater than, select the average, and we're using age again, of birth date from employees. So we have a subquery here, right? But let's break it down before we execute it, because we know this is going to output the right thing. So if we did age of birth date and we added it to the above query, what we're going to see happen is we're going to see the age of the date of birth, 66 years, 9 months, and 27 days. Great. Now, what if we add the average age? Well, let's take a look at that. When we select the average age, we're going to see, well, it's 61 years, 10 months, and 28 days. All right, so knowing that, we know now that the average age in the company is 61 years old. It's pretty old. Everyone's about close to retiring in this company. Great. But with knowing that, let's see what we can do. So in our where clause, we can say, hey, where your age is greater than the average age, show me those employees only. And when we execute that, what we'll see is that, hey, let's wrap this with age so we can see actually how old they are, because it's kind of hard to look at dates when it's like this. And we'll see that they're all older than 61 years old. Even this person is older than the average age. And let's put it right beside there just to make sure, just to see it again. So that was Kristinal. So when we look at Kristinal, well, 11 months and 23 days, and the average age is 28 days. So she is technically older because 11 months is greater than 10 months. So the comparison is working here. And we're comparing against the average age. So you can see here that the subquery in the where clause is extremely performant, easy to utilize that ability to run queries against other queries. Like, how would we have done this without a subquery? Well, it would have been extremely difficult, right? Because, well, we could have created a view where we had the average age, but then again, how would we go and compare against that? And if we use the window function, what exactly would happen? So it's an easy way to think about it, right? If we know that a subquery can return us one particular record, or it can return us a row set for the from clause, we know now that we can use it to easily write a query that will give us an answer. And it's always best to write out the query that works and then look at optimizing it. Don't try to optimize up front, because when you optimize up front, all you're going to do is confuse yourself. Queries are like a cake. You layer them. And I know I'm there again with my stupid analogies, but I'm trying to hammer it in that don't try to think too hard. Just try to write the query that gets the right answer and then try to improve it, because that is most important. Let's get a query that works and then let's learn from there. Don't try to get the most performant query. Don't let anyone bully you into, oh, you don't understand this concept. Oh, why didn't you use this? No, write the query that works for you and then figure out how to optimize it. That's the most important thing. So journey, it's not a race. So with that, we know now that we can use the where clause to calculate the age of someone. And then we can use a subquery to calculate with an aggregate function a single result, which is the average age. And we can compare those against each other because it's a single result. So we're comparing each and every individual row against the average age of every employee. And we could go even further. And if you said, hey, I only want the average age of all of the male employees, well, we can easily add a filter to the subquery and we can start layering those questions in and creating more and more complex filters. So this is a big thing for your filter game. This is like the level unlock that you haven't seen yet. You can build so many more complex where statements just because of this subquery, because you could write the query that filters out specific things, returns a singular result, and then compare in your where statement against something else. Like if we only wanted to know the average age of all of the males, we would say where gender is equal to male. And we could say the same thing in this where clause and so forth and so forward. And we're filtering down, first of all, the average age. And then second of all, we're filtering out the result set to only include the male employees. So you can see how you can layer in more complexity into your subqueries. Now, the second question I had for you was, show me the title by salary for each employee. And this is going to be an extremely interesting query to look at. So let's go take a look at it. Over here, we have a query, a very interesting query. And we're selecting employee number, salary, from date. And we have a subquery in the select clause. And we're selecting title. From titles, we're giving it an alias T. And we're saying where the employee number is equal to the outer employee number, because this is referenced as S. So we're creating what we would call a join here. We're saying where the employee number of the subquery we're trying to execute is equal to S.employee number. So we can reference from outside to in, but we can't reference from inside the subquery to outside. That's interesting. We can use data from the outer query. Interesting. This is what we would call a correlated subquery. This is a very interesting point because we are doing this right here, this where clause, where we're saying where employee number is equal to S.employee number, we're referencing from outside, right? And we call that a correlated subquery because the subquery is now related to its parent. It can't stand alone anymore without the parent query. We couldn't take this subquery on its own and now run it, right? Because if we did that, what would end up happening is we would basically run into an error, which is, what is S.employee number and S.from date? We don't have that. So we can't do that anymore. So what we end up doing is we end up creating a subquery that needs a reference to the outer query. Okay, so we're referencing outside T.employee number and S.employee number. So S is coming from outside. So we're creating a correlated subquery. It's a subquery that's related to its parent. Interesting. And so because we're selecting title from titles, and we're saying where the employee number is the outside employee number, and the from dates aligned because we need the title from that specific from date, well then, get me all of the salaries. So if we execute this, what we're going to see happen is we're going to get the title of each and every employee at the time that the from date matches. Okay, so what does that mean? Well, it means that whenever their title changed is when we're going to see an exact title, right? So we see here 10,001 started as a senior engineer and he got a bunch of raises, never got a title change. And then we had 10,002 that started as staff, and 10,003 that started as a senior engineer, and 10,004 that started as an engineer, and 10,005 that was staff, and so forth and so forward. And as we go along here, we can start seeing that we're basically seeing what was their starting title. That's pretty neat. And so the question becomes, how would this look and why do we need a subquery here? Well, we don't really. Like, this query is basically the same as us doing a left outer join. A left outer join being like, hey, show me all of the titles, even if the title never changed. And so it basically doesn't really help us, right? A join is faster, first of all, and it's returning the same results. So the subquery in this specific query to show the title per individual is a bad use of a subquery because we can solve it with a join. We can do the exact same output with a join. We could go even farther and just say, hey, do a normal join and just show me the ones that have a specific title on that from date. And that's even better because now I don't need to care about all of the times they didn't have a different title. We know their title and when they got that title. So that's pretty interesting, right? Depending on the type of query you're trying to solve for. And we just had that question, right? Get the title per individual. Well, we just saw that subquery was a bad solve for this specific query because we can solve it with a join. That's fascinating stuff. All right, the last query I have for you is the query you've all been waiting for. It's the query we've been looking at throughout the course. It's the ability to show the most recent employee's salary. So let's take a look at how we would solve that with a subquery. Here we are, the piece de resistance, the query that has kind of lingered on throughout the course because the way that we need to approach it evolves as we learn more concepts. We can solve it in many, many different ways. And so what we're trying to do here is we're selecting employee number, salary, from date, where the from date, and then we have our subquery here, going from here to here. And we're saying, hey, select us the max from date from the salaries where the employee number is equal to the outer employee number. Interesting. So what are we doing here? We learned this rule that subqueries are standalone queries, but now if I took this and I disabled this, well, I couldn't run this on its own, right? It would fail. It would be like, hey, what is S? I don't know what S is. So this is a very interesting scenario that we've put ourselves in, because what we've created here is, in essence, the correlated subquery. And so a correlated subquery, again, is a subquery that references its parent in order to have information to execute a more complex query. So the subquery is referencing the parent's information. So with a correlated subquery, of course, we're running this statement on each and every individual row, because as we process our data, we're going to be comparing the employee number from the inner result set to the data from the outer result set. And so this can be quite costly if we count this is going to take a while to execute because our subquery is not performant enough. And we've seen many ways to execute this. We did it with window functions and we did it with views. And so when we did it with views, we were able to do it with a join. And over here, we can see with a subquery, we're able to do it in the where clause and get an exact same answer. We're getting employee number, the most recent salary, and the from date. So we're getting the right answer. This is great. We got the right answer with the where clause and the subquery, creating a correlated subquery. Now, to refresh our memories, when we did it with the view, what we did is we had this view called last salary change, and we did something along the lines of join last salary change, and we did it using the employee number, because when we execute a query against this, and we open it in the SQL editor, what we basically have here is a query that's going to show us the employee number and the max from date. And we have a bunch of joins that we don't really need because we're not using that information, but just to say we're doing it and we're getting the max from date. So that is what this is returning. It's returning us two records and we're joining on employee number. And then we're saying where the from date is equal to ls max. So ls being the view, we're executing that. And we can immediately see that we're going to have to wait way less long than with the subquery. And we can prove this, and we can literally prove this. So we can see we're getting the same answer. We're getting the same information. And if we did an explain, analyze, and explain and analyze are two very important keywords because they tell us a lot about what our query is doing. They tell us exactly what the execution context is trying to do. So if we run this, what we'll see is what the query exactly is trying to do. And we can see it in steps. And you can go very deep into the query plan and looking into the execution context. And we can see how long it took it to gather and merge, when it's sorting, when it's working on something, when it's doing a join, when it's doing a sequencing, when it's grouping, when it's merging joins, and so forward and so forth. We can see all of that happen, and we can see the cost associated to that. For SQL to plan the query, it took it 1.5 seconds. And for it to execute the query, for it to go to the result, it took it 7.1 seconds. So 7.1 seconds to execute our query with the join. Interesting. But when we did our where clause and we said, hey, do it where, we select the max of the from date from salaries, and we do it where and let's give this an alias where sp.employee number is equal to s.employee number. So this was our original query with the subquery and the where filter. Well, let's explain and analyze that and see what happens there. And so when we execute the query plan for this one, we're going to potentially see less steps, but let's see what the execution time looked like, and let's figure out, hey, what exactly is going on here, and why is it less performant? And what we're going to end up seeing is, once this is done executing, well, we're doing a scan, we're getting the results, and let's see here, we're going through indexes. There's way less steps, right? Way less steps, but the where clause is going on each individual record. So just because it shows that it's doing less steps, well, it's doing a subplan. So it's calculating a subplan. So that's our subquery here. Interestingly enough, the from date, the filter, is going to apply itself to the subplan too, which the subplan is to execute this query. It's going to remove rows based on the filter. Whereas with the join, there were more steps, but it went faster. So how long did this actually take? Well, it didn't take very long to plan, as you would expect, because there's very little steps. We have a subplan, which is the subquery. We have our filter. So, very short planning time, 0.2 milliseconds. It's nothing. Very quick turnaround on SQL understanding what it needs to do here. But it took 18 seconds to execute. And so that's where you can shoot yourself in the foot, right? Understanding how to apply these queries is of extreme importance. This looks very simple. We can read this. It seems very legitimate, and, there's nothing crazy going on here. It's straightforward. You would think, this shouldn't take long, but because we're filtering, because we're using a where statement, and because we're using a subquery, well, we're applying that subquery against each individual row. So SQL can't go ahead and plan ahead of time. As you could see when it did the join, well, SQL can do some stuff in the backend to kind of figure out how it's going to join the data for you. It's doing more heavy lifting behind the scenes. A where clause is heavier up front, even though the query plan is way shorter. So how would, wait, Mo, you told us we could use subqueries anywhere in the query, and you showed us from, having, and all of these places. And you just showed us that we were using a view, right? With a view over here. And the view is nothing more than us querying against a query, right? So couldn't we do something like this? And just join a subquery? Couldn't we do that? Let's try it out. It should work. And let's name it LS for last salary. Most recent salary. Then let's name this max, just so that we properly name everything. So as LS. So we're joining as LS, and we're going to do a using. And we're going to use the employee number. Oh, wait. We don't have an employee number in our subquery. Wait. Subqueries, they can return a row set as well. They don't need to necessarily return a singular result. That's true. A singular result was only when we were using it in the select portion, or if we were using it in the where portion. When we use it in the from, we could return multiple rows. Would this be the same for join? Yes, it is. So we can do employee number here. And we can do a group by, which is necessary when we're using it together in combination with an aggregate function. Group by employee number. So if we group by the employee number, all right, we don't need this anymore because this was specific to using it in the where clause. So we're grouping, and we're getting the max from date for each individual employee. Amazing. So let's run this query on its own to make sure, we're getting the right results. So if we run this query, this is now a subquery on its own. It's not correlated, so it should return us the correct max from date. And we're seeing the correct max from date here. So it's basically doing the same as it did joining the view. So what that means is that when we join, it doesn't matter if it's a table or if it's a subquery, as long as it's a row set that we can join against, it should technically work, right? So if we do our where clause now and we say where ls.max equals from date, now we've done our join. And if we remove the explain and analyze for a second and we run this, we're going to get the exact same results as if we did it against last salary change. Now our query is less complex than last salary change, because if we open our SQL editor, our last salary change had a couple of joins. So those joins we don't take into account over here. We don't need them. We weren't using any of those columns. But if we run it, what we can see is we're getting the correct salary date, and it ran way faster. So if we do an explain and analyze of this, let's look at the explanation. Let's see what SQL is trying to do. Well, okay. This looks legit. It's a slightly longer query plan. It has 17 steps, and it's sorting, and it's hashing, and it's doing the joins and everything, and it's aggregating, and it's grouping, and all that stuff. But it only took 0.2 seconds for it to figure out what to do. So it took as long as the analyzing of the where statement. Interesting. It didn't take long for it to plan what it's going to do. But it only took 3 seconds to execute, as opposed to the 18 seconds when we ran the subquery in the where statement, because in the where statement, it's running and filtering against each individual row. It's going to execute that subquery for each individual row to make sure, hey, are you allowed to be here or are you not allowed to be here? When we do a join, our SQL, our Postgres is doing a lot of heavy lifting for us in the back, and we can see that in the query plan. We can see it in the amount of steps it needs to do. And if we went deep into what each individual step meant, we would deeply understand what is going on here. And at a high level, what is going on here is that behind the scenes, the join is doing the aggregation of the salaries table against the return from the subquery that we're executing right here. So it's joining the two result sets, the two tables in the background, and then we're doing our where statement against that return, against that joined data. So by doing that, we've simplified the amount of steps the query needs to take in order to filter out the data, because joining is way less expensive than filtering against each individual row while executing a query against each individual row. We're front-loading a lot of work to the query. And we can see that in the amount of time it takes to execute, because we're doing nothing different here than, for instance, if we were to run this against a view. This is basically the same concept, but it's very powerful to understand and know where you can put subqueries and how you can use them. Because again, the basic concept of a subquery is it can return a row set or it can return a single result. And depending on in which statement in the query you're using it, it may have to return a single result, or it can return a row set. And knowing that means it's so versatile to use anywhere. We can now join against it. We can use it in our from clause. We can use it in our where clause, and we can solve for so many different scenarios using subqueries. They are so extremely powerful. And with that, we now understand deeply how we can supercharge our queries, but also we understand now that, hey, making a wrong decision or not understanding how a query executes in a certain portion of the query can be costly. If we've put our subquery inside of our where statement and then executed it against each individual row, well, it started costing us a lot of execution time. Whereas if we put it in our join statement and we just joined against it like we did when we used the view and we joined the data sets, where we're front loading all of that work off to the engine, and we have way less execution time concerns because now our data sets are merged and we just have to do a simple comparison because we have the columns available, right? So you can combine subqueries with joins. It's not a big deal, but it's about understanding, hey, when do I need to use a join to make my query more performant versus when do I need to use a subquery to calculate something a bit more complex or create a data set, a row set that effectively has all of the data that I need, right? All right, so knowing all of that, let's look at some of the operators that we can use in subqueries and how to use them. To close it all out, I wanted to talk about the operators that you can use to apply in the where clause of subqueries. And the whole point of these operators is that they'll give you the ability to know how to operate against multi-column, multi-row, single row subqueries. They all have a specific purpose when running a subquery in your where clause. The first one is exists. And what exists does is it checks if the subquery returns any rows. So anything at all. Does anything come back from this query? That's what it's trying to tell us. And so when we write a subquery, when we write select first name, last name, income from customers as C, when we do where exists, what we're saying is, hey, a subquery is going to come in here and you're going to tell me whether or not anything comes back from it. And what we're trying to do in the subquery is we're selecting from orders. We're making it a correlated subquery. So we're linking the customer IDs together from the outer to the inner query. And we're checking if the total amount of that order was over $400. And then we're checking in the outer query if the income of that individual is over $90,000. So we're basically narrowing our funnel. We're saying, hey, can you show me all of the customers that make a certain amount of money that have ordered from us over a certain amount? So I could, for instance, target them with specific ads. That could be a reason to write this query. But the entire purpose here is to showcase that it's a correlated subquery and that the where clause is basically saying, hey, anything that comes back from here, if it exists, I want to know so that I can basically say which customers are available and then check if their income is over 90,000. So this is going to run against each individual row to check for each individual customer if they had ordered for over $400. Then the next operator is one that we've already seen before. It's the in operator. And the in operator is basically there to check if the value is equal to any of the rows in the return. Now, what we're trying to say here is that, hey, we're going to say for this column, check if it's in something. So for this one, we're doing a very, very, very simple subquery just to showcase and highlight what's possible. And for this subquery, the category yields a number 1, 2, 3, 4, 5, 6, 7, 8. And for all intents and purposes, we could have done in 1, 2, and 5 or 3, 7, and 8, but we don't happen to know what kind of categories are available. And the question was, hey, can you show me all of the products in the category comedy, family, and classics? So we wrote a subquery, which is a bit overkill, but in any case, we wrote a subquery that's going to return us the category numbers for the categories that are in comedy, family, and classics. And then the outer query is going to check if that number is in the numbers that were returned from this inner query. And one thing to note here is that with the in keyword, null yields null. If the value you are checking is trying to be validated against the null value, you'll get null. So if you're trying to check null against values, you'll get null. If you're trying to get 1 against null, you'll get null. Just be careful with null values. That's what we're trying to get at here. But in actuality, what we're referencing here is that in checks if any of the values are validated against that column and / row value. So the row value that we're trying to validate here is in a range of values that we're getting back from the inner query. And then not in checks if the value is not equal to any of the rows that were returned. And to the same effect, it has the same tendencies as the in operator. It's just checking the inverse. So you can see here that I use not in, and here you could also use not in, so you would get the inverse. I happen to leave it as an in, but not in basically would do the same to the outer query. It would inverse it and then say, hey, show me everything other than comedy, family, and classics. That's what would happen here. And then we have any and some, which are just the same but a different word. They're kind of comparable to each other. They're basically trying to check if any of the values relate to a value that is returned. So when we do this, if we say category is equal to any, and the way that you write any and some is that you write a column that is going to denote a row value, and then you use a comparison operator, and then you use any. And behind that, you run your subquery. And what this does is it checks against each row the operator, and if the comparison matches, it will return true. So it's checking against a range of values if any of them are correlated to that specific row. It's an easy way for you to say, hey, this subquery might return multiple rows, not a single row, but I still want to use my comparison operators. Because as you know, comparison operators can only be applied against a single record. So by doing this, what we're saying is we can use our comparison operators and we can check if they apply against any of the values. And if any of them match, return me a true. The inverse of that is all. It will check each row value against each row value from the subquery. And if all the comparisons match, it will return true. So if you have a multiple row situation where you're returning multiple rows from a subquery, with all, the value that you're checking must match all of the returned values. So let's say you were trying to check 1 against all of the rows in the subquery must return a 1, and it's going to validate against each and every one of those rows. So it's going to check 1 against 1, 1 against 1, 1 against 1, 1 against 1. And so with that being said, the multiple rows that are returned from here, they must all yield the exact same value that you're trying to check. In this specific query right here, you can see we're selecting product ID, title, sales, and we're joining on inventory so that we can have the sales value available. And then our subquery is in the where clause, and we're saying where the sales of the inventory are greater than all. And then the subquery is an interesting one. We're selecting the average sales, and then we're joining on the products, and we're grouping by the categories. So we're calculating the average sales for each and every single category. So we're getting basically all of the products where the sales were larger than the average sales of every category. So we're getting the top performers across all categories. So what this does is it's going to check sales against each and every row, which is multiple averages by category. And if the comparison is true, then it will return true. If the comparison is true for all of the records. So if sales is greater than each and every average for each and every category in this case. So all is also an interesting one. And so the final one, the final operator we'll be looking at are the single value comparisons. A subquery must return a single row and then check the comparator against that row. So as you remember, the different types of subqueries we saw, single row comparators where you're not using all, any, or some, when you use greater than, less than, equal to, and all of those comparators that we saw, they can only be checked against a single row. Here you see a very, very redundant subquery where we're just basically saying, hey, I don't know the number for the category comedy, so let me run a subquery and let me just get a single row back that is against comedy because I'm too lazy to look up the number basically. But in any case, the subquery must return a single row for this to work. If it returns multiple rows, the query will complain. And having shown you all of those operators, I think it's time to dive into some of the subquery exercises that we've prepared that you can try out. Have fun.